So electromagnetic induction is basically the phenomena in which an electric current is induced in a coil or a loop by changing the magnetic flux associated or linked. Where's the definition here, guys? Definition, I think in 10th grade also you might have learned at the definition, right? You change the current through one loop and automatically the current is induced to the second loop, right? Do you remember that? Hello.
Yes, sir.
So that thing is basically called as electromagnetic induction. It is the phenomena in which an electric current is generated in a coil or a loop is basically called as electromagnetic. Here, please remember the current so generated is called as the current generated is basically called as what? And please remember, if there is a current, then that current will be because of certain EMF, because we know, because without any potential difference current is impossible to flow, right? So the induced current should be flowing because of certain EMF generated throughout the coil. That EMF is called as, please remember guys, that EMF will be called as induced EMF. है ना? तो ये सब छोटी छोटी चीजें हैं, just remember them. There is induced EMF, there is induced current, right? Is this clear? Yeah, now थोड़े time बाद you will understand there is induced magnetic field as well. Always remember, ये सब बाद में करेंगे. Who gave these laws? Please remember there was a guy named what? What was the name of the guy who connected electricity and magnetism together? I told you, one guy was Oersted, who basically gave the magnetic effect of electric current. Now there was one more guy who basically gave the what? The reverse process. Basically, how you can create electricity with the help of magnetism, and that guy's name was basically Faraday. So write down heading Faraday's laws of EMF. The first law is basically whenever there is, guys, a little bit theoretical chapter will be there today because not much maths will be there. Relative source magnetic. That source of magnetic field can be either a magnet or a current carrying conductor, and it's up to the experiment. So whenever there is a relative motion between the source of magnetic field, the magnet or the current carrying conductor, and the coil or loop, then electric current gets induced in the loop because of change in magnetic potential. Yes, guys, you people are not speaking anything. तो कुछ बोल नहीं रहा है. So, what happens in this particular case? This is a non conservative electric field over here, which gets created. This non-conservative electric field it changes with respect to time. What is the cause of this being induced, right? You ask for the cause, right? What is causing this being induced? Yes or no? Hello.
Yes, sir.
See, थोड़ा सा
So,
cause जो
yes,
है ना,
sir.
the cause is ऐसे तो out of syllabus, but मैं फिर भी बता रहा हूँ आपको. The cause of being induced is basically the change in the non-conservative electric field generated in the wire or in the loop. So basically, the cause of being induced is basically the generation of a non-conservative electric field inside the loop. That in non-conservative electric field, this is an energy which gets produced out of study. But you know this particular thing, na, energy can neither be created nor destroyed, right?
Yes, sir.
So basically, this electric field energy which gets created is in the opposite phase of what the magnetic field energy is created in this case, right? Those two energies are intertwined with each other. That's why the term electromagnetic. Are you getting my point? So if there will be
Okay.
a change in the magnetic field, then an electric field will be induced. And if there is a change in the electric field, then a magnetic field will be induced. Right? So these
Yes,
two
sir.
fields are intertwined with each other. What happens when this EMF gets created? This EMF is because of a non-conservative electric field which gets generated inside the wire or inside the loop. Due to
Okay,
this
sir.
generation of electric field from this electric field should be generated from somewhere, right? This
So,
electric field it
how
should
is,
be generated from
yeah,
somewhere, right? So to
okay.
generate this electric field or basically this EMF, that induced EMF, sorry, the induced magnetic field comes into. Once
Okay,
more.
sir.
So basically to induce that EMF or basically to induce this electric field inside the loop, this has to come. Without this, this won't be there, and without this, the EMF will not be there.
Okay. Now, how is this EM, electric field there in the, because of the current?
Because not of the current, because see, it's like suppose if I am there, I am an electron, I am happy on my own, right?
Yeah.
But suppose you placed me in an external magnetic field. Now I am an electron, I am moving, and when I told a moving charge it produces a magnetic field of its own.
Yes, sir.
So I am producing a magnetic field of my own. Now what will happen?
Okay.
what will happen? You place me in an external magnetic field. So what will happen? My magnetic field and the external magnetic field will interact with each other,
Yes.
due to which I'll be subjected to a force.
Okay.
If I'll be subjected to a force, then that force will be responsible for me to move here and there, right? Or I can say
Yes, sir.
accelerate as well. So when
Yeah.
that force would cause me to accelerate to you, remember that particular thing? This thing. Uh, Accelerating charge causes electromagnetic waves to get formed, right? And what is
Yeah.
this electromagnetic wave? It's an electromagnetic wave. There is an electric field and a magnetic field
Either magnetic
intertwined
field
with each other, right?
perpendicular to
These
each other.
electric field, yes, electric field and magnetic field, they vary continuously in space. The change in electric field causes a change in magnetic field, and the change in magnetic field causes a change in electric field.
Electric.
So suppose
Okay.
whatever this thing which I discussed over here is not happening in space in vacuum, it's just happening inside a wire.
Okay, sir.
So are you getting my point? So here your electric field will not be directed up and down or something like that. It is directed throughout the whole coil. Matlab it is in the direction of the coil everywhere. It
Okay,
is,
sir.
say for JE advanced it's there, but even in advanced they are not asking questions based on that. So I was about to skip this E.dl wala, but we'll skip it. We'll not not study it in that much detail. But I just wanted
Okay,
to
sir.
know that there is, because of this, there is always a this magnetic field. Anyway, now this magnetic field induced, whatever magnetic field is induced, it should be because of certain current, right? Yes or no? Yes or no? So what is the last conclusion? Depending upon the direction of the induced, we can decide the direction of induced current. Okay. So tell me, if a B induced is acting in the outward direction, then what shall be the direction of current?
Um, like in the
And
outward direction.
In clockwise or anti-clockwise?
anti-clockwise.
Anti-clockwise.
Anti-clockwise. So basically, can you
Anti-clockwise.
see in the loop there will be current will be induced in the anti-clockwise direction. So this is the direction of induced current. Everybody got my point? How exactly we'll see? अभी भी मैं फ्लो चार्ट दे देता हूँ. How exactly you will think? First you will see cause, then apply Lenz's law, and then conclude. Okay? Is this clear, guys? This is how you will follow. I'll give you this thing. Someone will explain it to me. Okay? It's the same application, but what exactly am I doing? Yes, guys. What did I do this time? Did I
Decreasing
change the
the
number of
magnitude
turns?
of
So basically,
the
here
magnetic.
in this case, what did I did? I what did I did in this case? I decreased what?
The magnitude of magnetic field.
So in this case, B external is decreasing. है ना? So please remember in the previous case what was happening? B external was increasing. That is why phi m was increasing, right? So I want to decrease this phi m. Want to decrease. In the previous case, this happened, right? In this case, what will happen? B external will decrease. So what will happen? The magnetic flux will decrease, right? Hello.
Yes,
Yes,
sir.
sir.
Cause here in this case, what is the cause? The magnetic flux is decreasing because the external magnetic field is decreasing. Now apply Lenz's law. For B external, direction is this, and magnitude is decreasing. Suppose so here in this case, B external is acting in the inward direction and magnetic field is decreasing. To oppose the change, we want to reduce the decrease in magnetic field through the loop by increasing the net magnetic field. Yes or no? You can apply the same concept in the previous case as well. And to increase the net magnetic field, the loop will induce a current in what should be the direction of the current in the what should be the direction of the induced current so that the net magnetic field can be increased. So see,
Clockwise.
the same if I apply the magnetic field in the same direction, so can you see over here? This should be the direction of B induced. B external was acting like this, and since B external was decreasing, that implies B induced is also applied in this direction. So that can you see B induced and B external are both in the same direction. When both of them are in the same direction, then automatically can are we reducing the change by supporting in this case? Are you getting my
Yes, sir.
point, guys? I'll give you more examples. Don't worry. This is just the beginning. This is one or two times, because we have just started with the application. There are many applications like this. So B induced will be in the same direction. If B induced shall be in the same direction, what shall be the direction of current? So the current in this case, induced current in this case will be for B induced to act like this. I induced will be in the what about sense? Is this clear, guys? Is this clear? Current.
Yes, sir.
Cause, Lenz law, and conclusion. Is this clear?
Yes, sir.
We'll do one more. Don't worry. We'll do many more. This is just the beginning. So whenever you're done noting down, just tell me. And so the next application. A little bit of maths is involved, okay? See, in this case, what exactly I did. Everyone is able to see a loop, right?
Yes, sir.
So the question is somewhat or application example, whatever you want to call it. The question is initially there was a loop of radius r in a magnetic field B. Okay. In the next case, what did I do? I made this loop as then the next case, what I did, I made this as a loop. So the question is, the shape of the loop is changed from a circle to a square. Now the question is, so guys, can you see the shape of the loop? I'm just changing the shape of the loop. If I change the shape of the loop, then tell me whether how will you approach towards this particular type of problem? Can anyone tell me how will we approach in this particular type of problem? Can you see this magnetic field? I have not changed the magnetic field in this case. Did I change the magnetic field's magnitude?
No.
Did I change the direction between area vector and all?
No.
Did I change the number of turns?
No.
So in this thing I changed what? In this thing I changed the area, right?
Yes,
So
sir.
by
Yeah.
changing the area, I'm changing the flux. So see over here. What is the area of the first case? Will it be equals to pi r square?
Square.
Yes, sir.
And what is the area in the second case? Will it be equals to
L
s
L
square?
square.
Now I told you this particular thing. I just changed the shape of the loop. Did I change the length of the loop?
No.
So since the length is same, since I want to know whether I increase the area or decrease the area, accordingly I'll apply the length law, right? So see, if the length is same, then can I say twice of pi r should be equals to 4 times of x? Can you see the circumference should be equals to the perimeter? If the length has to be same, if the length of the wire has to be same, then can you see over here? 2 pi r is equals to 4, right?
Yes, sir.
So now what will happen? From here, I just want to get it in any one particular time. So r will be equals to twice of L by pi. Yes or no? Yes or no?
Yes, sir.
And can I put this over here? Pi. twice it and that. So from here it will become 4, 5, 5. Okay. Is this your A1 and is this your A2?
Hmm.
Now can you tell me which is greater, A1 or A2?
A1 is greater.
So basically, finally you are decreasing the area, right? Yes or no?
Yes, sir.
So by this and by this, the area is decreasing. If the area is decreasing, then automatically the flux will
Decrease.
decrease. So do I want to decrease the flux?
No.
I want to increase this decreasing flux.
Hmm.
So to increase this decreasing flux, what shall be the direction of being induced? Shall it be in the same direction or shall it be in the opposite direction?
Opposite.
In case of opposite direction, yeah,
Same direction.
same direction, no? Opposite direction is when it is increasing. Okay? Abhi I'll write the
Sorry,
note
sir.
as well. To increase the decreasing flux, the induced should support the external. So the external is acting in this direction. That applies the induced also should act in this direction. That applies the current should be
Clockwise.
flux. Please remember this thing and so the next case is basically the phi m will decreases. Then to decrease this, reduce this decreasing. So when phi m is decreases, then to increase this decreasing phi m, the external should support the induced should be in. Now is the thing clear, guys? What is the concept? How to apply the lens law? Okay, please write this. Then we'll do some more cases. I'll give you one more question. But today, at least we'll do all the application of lenses law, and then we'll work on the magnitude as well. We'll come to the cause of electromagnetic induction over here. Don't worry. At least I'll brief that. I'll make you write though that in proper words. That E dot ds thing. E dot ds था कि E dot dl था? I think E dot dl. Sure. Guys, whenever you're done writing, just tell me. This note is very important. This note will be your key to decide will they be in the same direction or will they be in the opposite direction. And depending upon the direction of being induced, we'll say the induced current is clockwise or induced current is anti-clockwise. Is this clear? Is this clear, guys?
Yes, sir.
Okay. So is this type as clear as well, right? Guys, is this type clear? When I'm changing the shape, then accordingly you need to do identify what will be the direction. Now the fourth type is something like this. Suppose there is a magnetic field over here. There is this loop. Okay. Hello, guys. Now what did I do? I wrote. Can you see the same magnetic field is there? But now what I did, I rotated this loop by 90 degrees. Yes, guys. Then if I rotated the loop by 90 degree, what will happen? Hello. Here, guys, what did I change? Did I change the magnitude of area?
No,
Hello.
sir.
Did I
Angle.
change the exactly? Here I changed the angle. Are you getting my point, guys? If I change the angle, then what will happen? Automatically the flux will change. Can you see in this case the magnetic field lines were crossing the area, right? So here there was some magnetic flux in this case. Here in this case, none of the magnetic field lines will be crossing the area, hence the flux over here will be phi m is 0 in this case, and in this case phi initial is something. And what will be that something, by the way? That something will be equals to n into b into a. We did these type of problems in the previous lecture, right? When we rotated the loop and all. Did we
Yes,
discuss
sir.
these type of problems? So
Yes,
phi
sir.
I is basically this.
180
Can you
degree,
see over
180
here?
degree.
From something initial to final, when we are talking about initial to final, can you see phi m is decreasing? Yes or no? Yes or no?
Yes,
Array, yes.
sir.
So basically in this case what will happen? Will apply the current will be induced, should try to increase flux. Okay. Suppose if I'm seeing this from the top. If I see this from the top, then magnetic field will look like this diagram. Guys, can you start looking from here? If you start looking from here, so can you see magnetic field which is going into the plane looks like this? The
Sir?
loop looks like this. Can you see the loop looks like this? Initially, the area vector and the magnetic field vector are in the same direction. But in the next case, what happened? In the next case, what happened? Final case, the direction of magnetic field is still the same. But can you see the loop becomes like this? Yes or no, guys? Are yes, sir.
Yes.
So basically, with the
Yes,
help
sir.
of this thing, the loop was decreasing, the flux was decreasing. So what I will try to do, can you see this loop is trying to rotate in which direction? The loop is trying to rotate in which direction? The loop is trying to rotate in which direction?
Clockwise.
The loop is rotating in this direction.
Yeah.
Yes or no? So what is
Yes,
the
sir.
external torque's direction is? Clockwise. Yes. Yes or no? Yes or no? So the torque due to induced current should be in. Are you getting my point, guys?
So in the first case, the flux can be positive or negative, right?
As well as zero as well. Here in this case, no, I'm taking the area
Yes.
vector into the plane. I'm
Okay,
taking
so we
the
can take it to be in any direction.
generally we take it into the plane because wherever it is decreasing, then the EMF has the same direction as it.
Okay.
Direction of area vector generally we take it in the direction of it. Initially, if nothing is given, then we take it as in the same direction. If it's not given and they have specifically mentioned, then you need to do it like that. Okay. Abhi here in this case, suppose I have given this okay. So
So I have a doubt.
follow.
So in the first diagram, you had marked a direction. What is that and what is this direction?
What does that direction and what does this direction? I rotated the loop about this axis, right?
Yes, sir.
Here the magnetic field was pointing into the plane. Area vector was also pointing into the plane. So initially the direction between both of them was same. So when I was looking from the top, it was looking like this. Magnetic field acting into the plane, area vector acting into the plane, magnetic field is also acting into the plane. And this loop is rotating.
No, 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 sir, not that direction. Along the axis you've marked, right? The
This
rotation's direction.
this one.
Yeah, that one.
Achha, are you saying
And
I made it in the wrong direction as I could?
yeah, I'm getting confused. There it's something else. In the next diagram you've marked some
Yes.
other direction.
I wanted to rotate it clockwise, right? Is it fine
Yes,
now?
sir. Yeah, it's fine.
So, are you getting my point, guys? This is the direction of tau external. So, what is the direction of torque induced? Can you see the senses? Hello. Is this example becoming a little typical? The induced torque should be this direction. So, for that, tau induced should be equal to n induced cross t. So, can you see, guys? N induced. So guys, can you see in this case, if I do the direction of induced m in the same direction as this area vector, so can you see because this m induced the induced torque? Hey, wait a second, guys. Phi m was decreasing. I wanted to increase it, right? The both should be in the same direction, right? I'll repeat this example again. See, basically the question was when I was rotating this loop clockwise by 90 degree, then what is the direction of induced current? Okay. So initial flux was something, and then when you rotated it by 90 degree, the final flux became zero, right? So that implies the flux was decreasing. When the flux was decreasing, then current should be in such a way, in such a direction that will increase the flux, right? Can you see this is decreasing? According to Lenz's law, we would like to increase this thing. And how will we increase this thing? Can you see the torque due to this thing was clockwise? If we can apply the direction same in the same direction as the torque due to the external limit. then automatically will be increasing the flux. So for that we applied the same direction torque, and hence this should be the same direction. And for M to be acting in this direction, guys, M induced to should be acting in this direction, right? But for this to be acting in this direction, should the current through it or induce the current through it, shall it flow like this? It's a loop, है ना? Please remember, it's a loop. It's a loop like this. We want M induced to be in this direction. So for that, the current induced should be like. Is this clear, guys? The direction. थोड़ा सा दिमाग लगाना है. This angle thing will make you a little bit troubled. Rest every other example will be same. Very easy. Is this clear, guys? This one will be typical, and please remember, थोड़ा सा this will be like a little bit additional. Need to put your brains a little bit more harder in this. Rest every other case will be easy. Have you noted down this one?
So it's not so torque induced will also be an anti. It will be also clockwise. Yeah.
It will be also clockwise. So for inducing the same type of torque, the direction of current should be in the same direction as what it was going. Right? And here I need
But
to
sir,
show the current as well.
because it's moving in like 90-degree in clockwise,
Hmm.
so if it has to be brought, it should be opposed, right? So shouldn't again come back in anti-clockwise
Huh? What?
because it's going in clockwise. The loop is there in the plane and it's going torque. It's moved in 90-degree in clockwise direction. So it has to be opposed and brought back, right? So it shouldn't be in the opposite,
But
like anti-clockwise.
it should be in the opposite direction. But the point is here, due to the rotation clockwise, it was decreasing. M was decreasing, right?
Yeah, it is decreasing.
If M would have been increasing, then we would have done that, which you are telling. Then we would have opposed the rotation. But since it was decreasing, that's why we have to support the rotation.
Oh,
Right?
okay. Oh, yeah.
There are two
Okay.
different cases. Okay. Chalo, next case I'm giving you. ठीक. The fifth मैं दे रहा हूँ. Suppose can you see a loop, guys? Guys, can you see a loop?
Yes, sir.
Yes, sir.
Yes. Can anyone tell me what is the direction of this loop? And basically, what does this part indicate? What does the solid part indicate, and what does the dashed part indicate? Huh? What does the dashed part indicate, and what does the solid part indicate?
Does the dash means it's into the plane?
Dashed means basically behind the plane. So you are not able to see this dashed part. You are just able to see the solid part, right? When you are sitting from here and looking at the wire, then the solid part it's coming in front of you. So now you understood, guys? Hello? Dash part and solid part. Now suppose I have a magnet. This magnet has a north pole over here and south pole over here. The same thing will happen to a solenoid as well, na? Guys, the same thing will happen to a solenoid as well. And my question is, if the magnet is brought closer, to this, can you see the magnet's north pole is brought closer to the loop? The direction of induced current should be. Acha, what the direction of deflection? If magnet is brought closer, the first case. second. Broader. Find the direction of deflection of galvanometer. Initially, the galvanometer is pointing at 0. If it deflects towards right, that implies it deflects towards B, है ना? And you will need to tell me the direction of deflection of galvanometer, or in fact direction of current through galvanometer from A to B and B to A, है ना? So your answer should be either A to B and B to A, like that. चलो शुरू हो जाओ. Apply a logic very well. Let me also apply the logic. Not pull is over here. Uh, uh-huh. Uh-huh. Excellent. ठीक है. Diagram is only for the first. Yes, guys, what is the direction? First case. First answer. A to B, B to A. Achha. Can anyone tell me what is the direction of magnetic field on the axis? Guys, hello. Can anyone tell me if this is a magnet, then this magnet will be producing magnetic field like this, right? Are yes or no?
Yes, sir.
So this magnet will be producing a magnetic field like this. Now what will happen if this magnet, can you see over here, due to this magnet, there is an external magnetic field like this on the axis. Yes or no? So where the coil is located, there also this external magnetic field will be in the same direction, right? Guys, do you remember electric dipole? किसी को याद है electric dipole? Plus Q, minus Q, and you know the direction of P was in this direction, right? And on the axial line of this electric dipole, whether it's a point over here A, then it's in the same direction, and here also at point B, it's in the direction of electric field is same, right? Yes or no? Do you remember this from electrostatics?
Yes, sir.
Basically, what will happen over here? In this case, this is just a magnet is nothing but a magnetic dipole. So can you see over here? If I just so when the north pole of the magnet is brought closer to this particular thing, that implies the B external is at this particular in this direction, and when you are bringing it closer, this B external is. So now you understood the cause. Yes or no? Everyone understood the cause. By bringing the magnetic field, what will happen? B external will increase, right? And if you want, I can do all the cases for this. So if B external is increasing, what do you want? I want this B external to decrease, right? And for that, what will I
Yes,
do?
sir.
I'll apply the induced in what direction?
Opposite direction.
So basically, for decreasing B external, shall I apply the B induced? For B external is in this direction. To decrease this thing, I'll apply the B induced in this direction. Yes or no? And for B induced to this direction, your thumb should point towards right. So can you see the current should come out of the plane at the topmost point and it should go into the plane. Yes or no? And from here, the direction of current will be from. Is this clear?
Yes, sir.
So this should be the direction in the first case. The current should be flowing from A to B. Okay. Now in the second case, what will happen? Yes, can anyone explain me the second case? Suppose that this is the coil again. Let's have a galvanometer placed over here. This is point A, this is point B, and this is your magnet. But in this case, I'm moving the magnet away with a velocity v. So can you see in this case what will happen? The B external due to the magnet was in this direction, right?
So,
So here where the loop is there, B external will also be in the same direction. But can you see as the magnet is moved away, here in this case, B external is decreasing. Yes or no?
decrease.
If it is
Yes,
decreasing,
sir.
then what will our B induced do? It will say, no bro, I won't let you die. And I'll support you. So can you see when it tries to support it, then B induced shall be in the same direction. Now your thumb should point towards left,
Clockwise.
left. So hence
Left.
the direction should be like this, or basically clockwise as seen from left, right? As seen from where the magnet is, right? Yes or no? Everyone got my point?
Yes.
Achha. So I think this case is pretty much clear to you. Acha, tell me these two. Suppose if I give a third case like this, um, and one case I'll give as a homework. Yeah? Now I have reversed the polarity. And can you see the magnet is moving now, still moving in the same direction? And magnet is moved away. Then how will you do this case, guys? How will, yes, Joysha, can you please explain?
Yes, magnetic external magnetic field will be from from into the to the right side.
So even where the loop is there, the B external is towards right. Now tell me what? Is this increasing? Is this decreasing?
It's decreasing.
So it is decreasing. So what will our B induced say now?
We're supposed to increase it, so it should be to the right as well.
So B induced should be in this direction. So B induced in this direction. Hence,
Current will be anti-clockwise.
like this. Anti-clockwise as seen from left, from where the magnet is. So can you see over here? Is this clear, everyone? Is this clear, everyone? Guys, did you see how we discussed? The red one is basically the cause. Then this, can you see over here, the red to blue shift is basically the red to green shift is basically the application of Lenz law. And then the conclusion part is with the green, right? So can you see? Red part is the cause. The red to green shift is basically the. Can you see? It's a Lenz law is a 3-step process. Is this clear? Is this clear, Akshay?
Yes, sir.
Shall I give you one last question?
Yes, sir.
Last application of Lenz law, suppose. Can you see a loop, guys? This is our primary coil, which is because due to which we are creating the magnetic field, and there is a variable resistor in this case. Battery is EMF. Now here you have another secondary coil. Can you see a secondary coil? Now question is, if R is decreased in primary coil, find the direction of induced current in secondary coil. Is this clear, guys? We need to find the direction of current in the secondary coil. Analyze it proper. I can ask anyone. Just give me 2 minutes. I'll be back. Hello, people. Yes, tell me. Satwik, are you able to? Hello, Satwik, are you able to say anything? Is your mic working properly? Hello, I think no.
Do you
Hello.
need the direction in which the primary coil is being moved?
No, the primary coil is not moving. We are just decreasing the variable resistance. No, nothing movement. Nothing is moving. Okay. Yes. Who will tell me? Arya, would you like to tell me? Hello, Arya, are you here? धैर्य समझाएगा भाई. Hello, धैर्य.
Yes, sir.
Yes. Would you like to explain me? Yeah, Arya, I was talking about
Right.
explaining this thing, but now I have asked Dhairya. If he couldn't do it, then you have to do it. Yes, tell me. लगा दिमाग गलत लगाएगा चलेगा. I don't mind. दिमाग लगा बस. Use brain. बता what you are thinking. No, mic is not. Okay. Okay. Yes, tell me. Dhairya, कुछ दिमाग. सबसे पहले बैटरी लगी हुई है, रजिस्टर है, तो क्या होगा? What shall be there?
Current will flow.
हाँ, तो करंट को फ्लो करवाओ, तो दिस इज योर करंट which is flowing in the primary coil. Yes or no? So now
Yes,
due
sir.
to this current, can anyone tell me what will be the direction of magnetic field due to this current in the primary coil? Will it be towards left or towards right? These two coils are coaxial. Okay? So don't worry. Can you see? I'll draw everything. Whatever the cause is with red, then the shift will be there, and then the conclusion will be there. So yes, I'm still doing the cause. Can you see? Because of the current, there will be a magnetic field produced by this primary coil. Yes or no? Yes or no, guys?
Yes, sir.
So what will be the direction of that magnetic field? Will it be clockwise, or will it be towards light, or will it be towards left? Yes, Navina. Navina here. Yes. Navina, can you
Yes,
please
sir.
tell me what will be the direction of this magnetic field created due to this current?
So will it be to the right?
It will be towards the right. No, it will be towards the left.
Left, right?
It will be towards the left. Can you see the current which is coming out? This part is out of the plane and
Yeah.
this part is going into the plane. So when you move
Yes,
your
sir.
fingers like this in the direction of this loop, can you see? From the bottom, you need to carry your fingers outwards of the plane and then go into the plane, right?
Okay. Yeah. Yes, sir. Yeah. Okay.
Like this.
Yeah.
Okay, so can you see it is pointing towards left?
Left. Okay.
So this is the direction of the external. And this is the last question, but very I'll give you. So this is the direction of V external created by this coil, right? So everywhere on the axis of this coil, this will be the direction of V external. So now the direction of V external has been decided. Now tell me, if you are decreasing resistance, will this current be decreasing or increasing? This E is constant.
Will increase.
So the
Current will increase.
current will increase. Due to this current increase, the magnetic field produced by the this thing will increase, and due to this thing, this magnetic field will also increase, right? Or obviously, guys, please remember the magnetic field strength over at the center of this coil and over at this distance will be different. But we don't want that. We just want what? What is the direction? We're just trying to apply the direction of length. Okay? So B external is decreasing now. See, B, this is the red one is with the cause. Now what to do? We need to oppose this increase.
Increase.
If I want to oppose this increase, what shall I do?
Decrease it.
Yeah.
To decrease it, के लिए
Be
what shall we
induced.
do?
Be induced in the
induced.
opposite direction.
The opposite
Very good.
direction.
So B induced should be in this direction. If B induced is in this direction, so can you see? So from the bottom it is going into the plane and from the top it is coming out of the plane. So basically this is this clear? This should
So
be
can
the
you
direct.
please repeat it?
Sure.
Your
Due to
voice
this,
broke for me.
okay. So can you see over here the B induced is towards the right? Yes. So from when you apply right hand thumb rule for the magnetic field, first law RSTR. So can you see from the bottom of the loop the current is going into the plane, and then from the top it should come out of the plane. Then only the magnetic field will be acting towards right. Yes.
Yes, sir.
So basically we applied the law and hence we got the direction. So the I induced shall be in the anti-clockwise direction as seen from right. If you are observing from here, then can you see anti-clockwise it is done? Okay. This is the answer. So I hope application of lenses law is pretty much clear. If not, please refer to the video again, guys. एक बार देखो. And if you have any doubts, you can always message me. Okay? We'll see you again on Thursday, and we'll finish up with something. Okay? Chalo, okay. Thank you, guys. We'll see you again. Hello.
Thank you, sir.
Chalo, bye-bye.